At any moment, lightning will strike the Earth 1,000 times a second, and countless storms will tear through the atmosphere. Yet these phenomena are but fleeting glimpses of a far more powerful force. Today, a global search is underway to unravel the mysteries of Earth's climate. Over time, the climate of the Earth changes as dramatically as the seasons. But only now are scientists beginning to find out how and why. This is the story of their search. It begins with the fragments of a giant puzzle collected from around the world. An incredible saga is beginning to unfold of droughts and searing cold, of warm spells and eons of ice. The pieces are everywhere, in the corals of a Caribbean paradise, and beneath the sands of India in the pollen of simple plants. They can be found in a limestone cave in New Zealand and in the high reaches of the Swiss Alps. There are pieces of the puzzle in stones of an Antarctic desert and in the shells of microscopic creatures found at the bottom of the sea. Even in these skyscrapers of clay on Africa's plains, tiny creatures that far outnumber humankind are helping to change the air we breathe today. In a citadel of climate research in Colorado, scientists have created an electronic crystal ball. With it, they can plot Earth's ancient climate and peer into the future well beyond our lifetime. The picture now emerging is one of dramatic climate change that will affect all of us on planet Earth. Join us now on an intriguing journey across time and continents as scientists piece together the puzzle of Earth's changing climate.
Annenberg Media.
Corporate funding for Planet Earth is provided by IBM. IBM is proud to support the innovative spirit of scientific inquiry that made this series possible.
Amid a land of great ice lies the strangest desert in the world. 200-mile-an-hour winds and temperatures 100 degrees below zero make the dry valleys of Antarctica one of the most inhospitable places on Earth. Here, an unusual tale of climate and life is unfolding. Not even the sophisticated devices we have sent to explore other planets could have found what scientists have found here. Each Antarctic summer since 1976, researchers have come here to study a primitive form of life found nowhere else on Earth. The climate of Antarctica is so hostile, it has driven life to take refuge inside, among the pores of ancient rock.
Rick, I'm going to chop off a piece of this rock and show you.
For a scant 5 days each year, the sun warms the rock enough for tiny organisms to break their slumber of frozen quiet. From the rock itself, they take nourishment, and from the air, bits of scarce moisture. Quickly, they reproduce, then become dormant until next year's summer sun wakes them once again. A mere 1/10 of an inch below the surface, the microbes are safe from the vicious climate. Each dark band is a miniature ecosystem. Long strands of fungi and clusters of algae join to form the lichen that grows among the rock crystals. The microbes actually change their shape to fit this unusual habitat. To learn how life can exist here in this extreme environment, the scientists provide nutrients to the organisms.
Organisms grow so slowly that they may be deficient in some of these essential nutrients. So over a number of years, we may see a stimulation in their growth.
In another experiment, the scientists create artificial greenhouses to lengthen the microbes' growing season. They want to know how life will change as climate changes.
And if we leave these guys out for 3 or 4 years, the heat created by the greenhouse effect should warm up the rock so that hopefully the organisms will have a better chance of growing.
Here, in the most barren environment on Earth, life fits inside nearly every loose rock. It now seems clear that life on Earth is dramatically shaped by Earth's climate. Through eons of evolution, the great array of life on Earth has developed strategies to cope with a changing climate. Driven by some mysterious internal time clock, some birds travel thousands of miles each year to escape the onset of winter. Animals that cannot flee meet the challenge of a climate turned extreme in numerous and ingenious ways. They adapt by foraging or hibernation. The great chain of life reflects the continuing drama of Earth's changing climate. The fate of human endeavor may also be linked to our inconstant Earth. An unusually benign climate coincided with the rise of civilization, perhaps even fostered its development. Indeed, civilizations first flourished in regions that are truly harsh today, in the searing sands of the ancient Middle East. The inescapable effects of climate change also may have been an important factor in human upheavals throughout history. South of the Himalayas, where India meets Pakistan, lies the great Rajasthan Desert, the most populated arid region on Earth. For thousands of years, people have scratched a living from this bleak world. On sparse desert grasses, they raise domesticated animals and carefully guard what little water can be found. Here, water is more precious than gold. It comes but once a year. For weeks at a time, the monsoon lashes India with steady sheets of rain. Usually, summers are wet and winters are dry, but the monsoon reverses the pattern. The monsoon has fueled the Indian breadbasket for millennia. Deep in the Rajasthan desert, these temples at Ossian bear mute testimony to the spiritual values of an ancient and prosperous civilization. They are symbols of the many cultures that have disappeared, caught in the vagaries of time and climate. As archaeologists recover the ruins from the sands, so too have scientists discovered an archaeology of climate. The ancient city of Lothal, once the seaport of the Harappan culture, now landlocked by the desert sands. For 1,000 years, the Harappans prospered here as farmers and distributors of grain. Then, mysteriously, they disappeared.
Well, we do have a prediction.
Climate historian Reed Bryson of the University of Wisconsin is an expert on the monsoons. His advice is critical to the region's farmers.
We'll have above normal precipitation.
Bryson has also wondered about the disappearance of the Harappans. Many archaeologists believe they had been weakened by a succession of invasions. Bryson's curiosity led him to Sambar Salt Lake, where he found another answer.
Stratified lake sediments like this are like a book in which the history of the climate of this region has been written. Because in those layers, each year in its history over the last 10,000 years, plant pollen, sand, various things have blown in and accumulated. And we now know how to look at that assemblage of various kinds of plant pollen and charcoal and sand and interpret it to read the writing of history in this lake sediment.
The layers of pollen have revealed a prolonged drought, a time when the monsoons failed and the Harappan culture collapsed. 250,000 people may have perished in the desert. Today, hundreds of millions depend on the return of the monsoons. The study of ancient civilizations reveals that the past can leave long shadows that affect the present and the future. The records left in the Rajasthan cover but an instant in the history of Earth's climate. In a limestone cave in northern New Zealand, the slow drip of water has created a much longer record. Here, scientists have become explorers. With headlamps and protective gear, they seek to push the climate record back further in geologic time. Geochemists Chris and Vivian Hendy.
This is the spot here.
This is where we set up the plastic tubing to collect the water for the radiocarbon dating.
And the next problem was we had to find a stalagmite or stalactite which would give us a suitably long time record for oxygen isotope analysis. Now, if you took these straws, they grow 2 or 3 meters, then they drop off. It's better if we go to stalagmites. Now, here we have a very large one underneath us. This is Mount Egmont.
As water and minerals seep through the ground above, they create the delicate architecture of the cave. Some minerals deposited when the climate was cold differ from those deposited when it was warm. The minerals actually create a chemistry that can be extracted as an historical record of the world's climate. Drip by drip, the cave forms before our eyes. Formations like these have been created over tens of thousands of years, and with them a perfect record of change in temperature and moisture of the past. Concerned about preserving the fragile beauty of the cave, Hendy and his party have hiked a mile through ankle-deep water to look for a specimen that can be removed for analysis.
Right, now there's the one we finally took. It's out of the way. It was a stalactite that was already broken. It eventually went down to about here. It was probably part of a column that was joined to the floor, but the floor dropped away and left this broken stub. So we had a full 100,000 years record from one side through to the other. Now, I'd like to take a sample.
Hendy collects water from these ancient stalactites. The mineral content helps him determine the age of the formations.
Chemistry and composition's been changing.
At Waikato University, Hendy dates and analyzes the limestone layer by layer. His research would confirm a history chronicled by the artists of another time and place. As Dutch artists created their famous landscapes, little did they know they were documenting a dramatic shift in Earth's climate. Today, the Dutch canals rarely freeze, but in the 17th century, more than 3 centuries of unusually severe winters plunged Europe into what scientists now call the Little Ice Age. 100 years ago, the idea of an ice age was inconceivable. A few intrepid scientists had suggested such a possibility, but they were largely ignored. In the middle of the 19th century, a picture began to emerge of a time when Earth's climate was dramatically different. A time when ice ruled the world. For hundreds of years, these towering walls and precariously perched boulders mystified all who saw them. Most thought they were swept here by the Great Flood, so vividly described in the Bible. But in 1837, another persistent observer had a different idea. It was here in the Swiss resort town of Neuchâtel that the ideas of a young scientist would ignite one of the most violent disputes in the history of science. Swiss naturalist Louis Agassiz shocked the scientific establishment when he declared that the world around them was once covered by ice, more than a mile thick. To support his theory, Agassiz pointed to the strange boulders. He matched their geology to mountains hundreds of miles away. The rocks were simply too large to have been moved by floodwater. Nearby, in huge sheets of rock, he found grooves and channels. Elsewhere, he observed bedrock that was amazingly flat, as if sheared by a giant knife. In his notebooks, Agassiz vividly illustrated a distant epoch of extreme cold when ice covered much of the Earth. He called it an Eiszeit, or Ice Age. What was a radical idea for science was obvious to those who lived and worked here. The chamois hunters of the high Alps had long identified the strange rocks as pieces of distant mountains that had broken away and were moved across the land by the glaciers. The lost rocks, like lost sheep, were called foundlings. Agassiz had heard these tales. From these simple and elegant intuitions, he would define his scientific theories. To convince others, Agassiz organized many field trips to the glaciers, a tradition still observed by scientists. These glacier walls are as dramatic today as they were then. To Agassiz, they were God's great plow that slowly but steadily carved and shaped the valleys below. Still more startling, Agassiz argued that glaciers were the remnants of a time when ice not only covered Switzerland, but stretched from the North Pole to the Mediterranean Sea. Each summer, scientists return to explore the glaciers of the high Alps. They hike among the rock and along ridges that so intrigued Louis Agassiz. A glacier is virtually a river of ice. With an imperceptible motion, it scours everything in its path. Like a river, it flows at varying speeds to create treacherous currents called crevasses. Hundreds of feet deep, they can disappear almost overnight, collapsed by the continuous onslaught of the ice. Nearly 1/2 of the Earth's landscape has been carved by such unceasing force. Eventually, we would come to know that not one, but numerous vast and regular ice ages have dominated the planet. For most of the last million years, ice was the normal climate of Earth. An ice age begins when summer temperatures fail to melt the snow from a previous winter. Year after year, the ice sheet grows. Only the tropical climate near the equator can stop its advance. Eventually, the Earth mysteriously warms up, and the ice begins to retreat. But what sets an ice age in motion? No earthbound theory can explain the causes of such dramatic shifts in climate. Intrigued by this mystery, Yugoslavian mathematician Milutin Milanković sought to develop an astronomical theory that would account for the ice ages. He believed they were caused by changes in the Earth's relationship to the sun. We have long known that the seasons are caused by the tilt of the Earth on its axis. But every 41,000 years, the Earth's tilt varies by a few degrees. Every 100,000 years, Earth's orbit varies from nearly circular to elliptical, moving the Earth millions of miles further from the sun. And Earth wobbles slowly like a top in space to complete a circle about every 20,000 years. The tilt, stretch, and wobble of Earth's orbit change the distribution of energy received from the sun. It was Milanković who calculated that these changes could trigger the ice ages. Without evidence to support it, his theory was forgotten until a serendipitous discovery in the Caribbean island of Barbados. At first, scientists were puzzled by the island's terraces that looked like giant stair steps. Eventually, they determined the terraces were actually ancient beaches because the terraces contained fossils of coral like those still found along the shore of Barbados today. Since coral grows only in shallow water, the terraces suggest that sea level was once higher here. Could the terraces reflect a time between the ice ages when sea level rose as the land ice melted? When the fossil beaches were dated, they appeared to match the astronomical cycles suggested by Milanković, a clue that his theory was right, adding one more piece to the climate puzzle. After World War II, scientists embarked on a global search for the remains of past climates on the ocean floor. A device called a piston corer is plunged through thousands of feet of ocean and into the muds along the bottom. The explorers would discover that the sediments on the sea floor held a record of the great ice sheets on land. In the laboratories, sea cores are unwrapped, time capsules from an ancient Earth. When the core is dissected, nearly 500,000 years of Earth's climate history is revealed. At the Lamont Doherty Geological Observatory at Columbia University, thousands of cores from around the world are cataloged and stored. They create an unrivaled library of the past. Geologist James Hayes has pioneered in the analysis of sea cores. Interpretation of these ancient records is a milestone in climate science.
Although the fact that ice ages had once occurred was first realized from studying the geology of continental surfaces, continents do not contain a very good record of the sequence of advances and retreats of the great ice sheets. This is simply because the continent surfaces are always being worn away, either by the abrasion of the great ice sheets themselves or by the action of rain, rivers, and wind. Now, all the particles that are washed from the continents eventually end up in the ocean, forming muds on the ocean floor, such as this core. These cores, in contrast to the fragmented record of the continents, contain a complete record of long periods of time.
The cores also contain the fossil remains of tiny organisms that thrived in the ancient seas. When they died, their shells rained down to become the sediments on the ocean bottom. Layer upon layer, these shells form a vast record of changing climate. The fossils of ancient marine life are carefully extracted from the cores. As these tiny glass-like shells are sorted and organized, they begin to tell a story.
These are the shells of microscopic organisms known as radiolaria. When living, these creatures are delicately adapted to the temperature and chemistry of the water in which they live. As climate changes and the temperature of the ocean water changes, different species are favored and flourish.
The distribution of radiolaria is linked to changes in the temperature of seawater. By charting temperature changes, Hayes and his colleagues found a cycle that matched the one suggested by Milanković.
Therefore, each ocean core can be viewed as a monitoring station which carefully records changes in the ocean water that lies above it. With many cores from all over the world, we can reconstruct global changes in the ocean that accompany ice age cycles.
By mapping the global temperature of ancient seas and connecting them with cycles in space, researchers have moved one step closer to a solution of the Ice Age puzzle. An ingenious method of analysis would reveal still another matching cycle. In addition to temperature, the chemistry of the ocean also changes during an ice age. The shells of marine organisms record this change. By comparing them through isotope analysis, Hayes can determine when the ice ages occurred. When the cycles of change in temperature and chemistry were plotted, it was discovered that both cycles matched those predicted by Milanković. Changes in the geometry of Earth's orbit are the pacemakers of the ice ages. New York's Hudson River is a striking example of the recurring phenomenon. James Hayes.
15 to 17,000 years ago, this valley was filled with a river of ice instead of the Hudson River. At that time, the ice in this valley drained the great North American ice sheet, which was rapidly retreating to the north. The question we must ask now is, will the ice one day return to this valley? The answer to that question is yes. For just as the change of the seasons are controlled by the geometry of the Earth's orbit around the sun, so also are ice ages. As fall will certainly change to winter, just as inevitably the ice will return to this valley.
If Hayes and his colleagues are right, planet Earth may face another ice age, which could reach its peak some 100,000 years from now. "800 miles from the South Pole is Vostok, one of several research stations manned by the Soviet Union in Antarctica. Vostok, which has recorded the coldest temperature on Earth, sits on the thickest part of the Antarctic ice sheet. The arrival of an American transport is a rare sight. This one has brought French glaciologist Claude Lorius, here to share in the celebration of an historic event.
I say three words.
You understand?
Ruski, Amerikanski, Franzuski, Vostok, Karasho.
In 1979, the Soviets began an ambitious project. Their goal, to drill through the 2.5-mile thick Antarctic ice sheet. The technique of drilling polar ice was first developed here in Greenland. In the ice is a litany of endless seasons, as layers of snowfall are compressed over tens of thousands of years. From the ice cores, scientists hope to learn more about the climate that has ruled planet Earth for most of the last million years. The mile-long Vostok core is unique. It contains 150,000 years of Earth's history, from the beginning to the end of the last ice age. Claude Lorius will spend the next 3 months carefully sectioning and preparing the core for shipment to France. At the Institute of Glaciology in Grenoble, he will begin the long and painstaking analysis.
Bonjour.
The Vostok core has survived a journey halfway around the world, yet even here it remains extremely fragile. Even the slightest alteration can destroy its unique value as a climate record. To safeguard the core, the laboratory is sterilized and maintained at temperatures below freezing. To eliminate contamination, only the heart of the core is used for analysis. Each layer is like the page of a diary. A mere sliver reveals new detail. Trapped in the ice is dust and ash, a clue to the action of long-dead volcanoes. More intriguing are bubbles of gas, whiffs of ancient air. Seen under polarized light, the ice becomes a kaleidoscope of color and form. Among these tiny crystals is all that is needed to determine the temperatures and chemistry of the atmosphere during the last ice age. One of the most provocative finds is a record of carbon dioxide in the atmosphere of the past. Coring has confirmed that the carbon dioxide level during the last ice age was significantly lower than it is today. How it got that way is still unknown. For Claude Lorius, there is a new urgency to the search.
If we want to understand current change of our terrestrial environment and eventually be able to predict future conditions, I think it is first very important to establish what were the past changes and see if we are able to understand them and explain them. I think this is a necessity if we want to make projection to the future.
Although the advance and retreat of ice seems inevitable, Earth's climate has remained surprisingly temperate over billions of years. Now scientists have uncovered another paradox. It appears our ancient sun was once smaller and radiated less heat than it does today. If the sun was faint, snow would gradually accumulate and the planet grow colder and colder. Eventually the oceans would freeze and Earth would become a glistening planet of ice. But there is no such evidence for this scenario. Liquid water, the basis of life, has existed on Earth for nearly all of its history. A clue to the mystery can be found millions of miles from planet Earth. When the first probes ventured to Venus and Mars, they discovered atmospheres fierce and alien to our own. Venus is hot and noxious. Nearly 900 degrees Fahrenheit at its surface, its rocks glow red. This hothouse climate exists because the thick acid clouds contain an extraordinary amount of carbon dioxide. Like the glass of a greenhouse, carbon dioxide traps heat and prevents it from escaping back into space. The atmosphere of Venus contains some 300,000 times more carbon dioxide than planet Earth. If long ago Venus had liquid water, it boiled away into the atmosphere of this hellish world. At the opposite extreme is Mars, a frozen planet. A land of massive volcanoes, its landscape is testimony to the violent activity that once may have pumped enough carbon dioxide into its atmosphere to warm the planet. The scoured surface of Mars suggests it was once warm enough for liquid water to forge deep canyons and river valleys and to carve great floodplains. But somehow Mars lost its ancient atmosphere, its liquid water disappeared, and what remains is a frozen, decimated world. Venus is a hothouse that cannot cool down. Mars is a world that cannot warm up. Extreme worlds of fire and ice. In orbit between Venus and Mars is Earth. Neither too hot nor too cold. It has an atmosphere with just the right amount of carbon dioxide for life to flourish. Unlike Venus and Mars, the Earth's surface is constantly changing, scoured by wind and water and torn apart by powerful forces within. The carbon stored in the Earth is continually recycled through the land, the oceans, and the atmosphere. Even life plays an important role in the cycle. This dynamic process helps control the amount of carbon dioxide in Earth's atmosphere and seems to resolve the mystery of our ancient sun. If there was more carbon dioxide in our early atmosphere, it could have trapped enough heat to keep the planet warm. Scientists now believe that abrupt changes in carbon dioxide can cause abrupt shifts in climate, perhaps even influence ice ages, and, like Venus and Mars, create radically different worlds. This understanding of the role of carbon dioxide is among the great insights of modern science. Now there is a new urgency to understand the role of carbon dioxide in the life of the planet Earth. Since the advent of civilization, and particularly in the industrial age, man has injected enormous amounts of carbon dioxide into the atmosphere by the burning of coal, oil, and gas. The techniques of slash and burn deforestation to create fields for farming releases still more carbon dioxide. A time bomb seems to be ticking in our atmosphere. The climate of Earth is maintained only when the amount of solar energy absorbed by the planet equals the amount returned to space. As carbon dioxide increases, it retards the escape of energy. Like a greenhouse, Earth's lower atmosphere heats up. Hawaii's Mauna Loa Observatory is an ideal laboratory for sampling the Earth's atmosphere. Here in 1958, Charles Keeling of the Scripps Institution of Oceanography developed a method for measuring carbon dioxide. Since then, carbon dioxide has risen some 9%. At this rate, it could double sometime in the next century and raise the mean temperature of Earth some 3 to 10 degrees Fahrenheit. Such global warming could lead to the most dramatic change in Earth's climate since the last ice age, a change far greater than any experienced by mankind. The predictions of warming are fiercely debated, but all agree we are performing a great experiment on ourselves and our planet. The results of a potential carbon dioxide warming may eventually be seen here. Since the International Geophysical Year in 1958, Antarctica has become a natural laboratory where the dynamics of ice are explored by scientists from around the world. Here, global warming would create a special threat. Most of the Antarctic continent is covered by ice nearly 2 miles thick. Much of it rests not on land, but in the ocean. It is unstable and susceptible to movement. Scientists are concerned. Could Antarctica lose its ice? They explore even the slightest change in the vast and complex ice cap. They map crevasse fields, great frozen rivers that slowly but steadily flow into the Ross Ice Shelf, a floating slab of ice the size of France. The Ross Ice Shelf acts as a plug. It holds back the huge mass of ice that covers West Antarctica. Warming could cause the shelf's leading edge to disintegrate and destroy the barrier that contains the unstable West Antarctic ice sheet behind it. If West Antarctica's ice sheet collapses and melts, sea level could steadily rise some 20 feet to dramatically change the geography of planet Earth. Venice, the crown jewel of the Adriatic. Latticed by canals that form its streets, Venice is often flooded by storms at high tide. If carbon dioxide were to substantially warm the Earth, such flooding could become commonplace. Even a small increase in sea level could cause havoc. Storm surges at unusually high tide would threaten coastlines more and more frequently. Eventually, cities would have to respond with dikes and barriers, like London has now installed across the Thames to protect it from tidal surges that threaten even now. But populous countries built on coastal plains just above sea level are most vulnerable. In 1970, 300,000 people died during a ravaging storm surge in Bangladesh. A warmer climate could change growing seasons and make temperate regions much drier. The breadbaskets of the world might shift. The Soviet Union could replace the American Midwest as the world's leading producer of grain. In countries dependent on irrigation, the warming could be devastating. Hotter, drier climates could put still greater pressures on now arid regions. Desert areas would expand. Those who depend on the world's rivers for water may well experience hardship. The Colorado River, which delivers water to America's desert states, already loses more than 3/4 of its supply to evaporation. Rising carbon dioxide would also act as a global fertilizer for green plants that thrive on it. Explosive growth could radically alter ecological balances that have evolved over billions of years. We know that climate shapes life. We can only guess at the impact on life from a rapid and major change in global climate. Still, there is a great uncertainty about the consequences of a global warming. Some undoubtedly would benefit, others would suffer. The consequences of a carbon dioxide warming are serious enough to be considered the most important challenge in modern climate research. At the National Center for Atmospheric Research in Boulder, Colorado, meteorologist Warren Washington designs experiments called climate models that simulate the atmosphere of Earth.
This is one of the world's fastest computers. It is able to do 100 million operations per second. We're able to do things that we couldn't do 10 years ago on the computer. For example, we're able to generate a computer model of the atmosphere that simulates the winds, the temperatures, the pressures, the rainfall, the snow cover over 23,000 points over the entire globe.
Simulating the dynamics of Earth's atmosphere is a complex task. The land, oceans, polar ice, even life can influence climate. External factors like changes in radiation from the sun can further complicate the model. The enormous speed of the computer manipulates the many climate factors. The simulated Earth is turned on and run for a few computer days to predict weather, or for years to predict climate. By changing the factors of the climate model, the scientists in Boulder can perform tests that are not possible in the real world. They explore the scenarios that might reveal the causes of global climate change. Climatologist Steve Schneider uses models to explore the possible impacts of a carbon dioxide warming.
The question we have to ask ourselves is, what are models good for? Why do we need them for the future prediction of climate? Well, if we're going to try to figure out what's going to happen in the future, we need to estimate how much greenhouse gas humans are putting in, and then we have to ask what that's going to do to the climate. Well, if you haven't got a physical model, a twin Earth, if you will, that we can go and pollute by adding greenhouse gases to and then see what happens, the only other model we can build that has any plausible hope of telling us about the future is a mathematical model, which we build and run inside of a computer. We take this model and we describe the present climate in it, essentially simulate the present climate. We then add greenhouse gases that humans are adding to the model, ask the model how has the climate changed, compare the two, and have some idea of what the future might bring us climatically if we did that kind of addition of gases.
While some scientists speculate on the future of carbon dioxide in the atmosphere, others test an intriguing scenario of climate in the past. Today, this semi-arid region is part of Colorado's Pueblo Reservoir State Park. But when dinosaurs ruled the Earth, it was covered in water. Searching among the ancient rocks for evidence of the ancient sea is geologist Eric Barron.
These rocks date from the Cretaceous period, about 90 million years ago. The characteristics of these rocks and the fossils we find in these rocks tell us that this area was covered by a broad, shallow sea The seas stretch from Colorado to Kansas and from the Gulf of Mexico to the Arctic Basin. If we look at the fossils, we see that they're distinctly marine. They indicate that the climate was much warmer than it is today. If we go to a place like Greenland, we find fossil alligators. And unless an alligator had fur, the climates must have been much warmer than they are today.
Fossils in the rocks tell of a place in sharp contrast with eastern Colorado's near-desert environment today. 100 million years ago, dinosaurs roamed here in what must have been a lush and tropical world. At the National Center for Atmospheric Research, Eric Barron uses a computer model to find out what might have caused such warmth in Earth's past. The position of the continents is adjusted to the time of the dinosaurs, and other climate factors are added to create an ancient Earth. Barron knows what it was like then. He must find out why.
The Cretaceous geography stored in this computer is clearly dramatically different than the present-day geography. We see, for instance, Australia attached to Antarctica, India in the southern hemisphere, and the evidence for flooding, for instance, here in North America.
His primary clue came from a new understanding of the planet's moving crust, from plate tectonics. Scientists have discovered that the Earth's surface is cracked and broken. In the middle of the oceans is an undersea mountain range where a fiery drama begins the creation of Earth's crust. Hot rock from the interior rises and spreads the sea floor to each side. The result over time is the movement of Earth's continents across the globe.
It's hard to imagine a more dramatic change in the surface of the Earth than what we see here. What is so incredible is that when we plug in this dramatic change in Cretaceous geography into a climate model, we achieve only 1/3 of the warming necessary to explain Cretaceous climates.
What caused most of the warming? At the sites where seafloor is created, explorers in deep-diving submersibles have found towering vents that spew gas and carbon dioxide into the ocean. Gases from the vents eventually escape to become part of the atmosphere. Elsewhere, seafloor is recycled back into the Earth along the world's deep ocean trenches. As the seafloor sinks into the Earth's interior, it melts. Carbon, locked in the Earth's interior for millions of years, rises to the surface and explodes in volcanic violence, once again enriching the atmosphere. By increasing the amount of carbon dioxide in his model, Barron can now account for the extreme warmth of the Cretaceous period. If the model is accurate, the rocks of eastern Colorado should reveal widespread evidence of volcanic activity.
Within these same Cretaceous rocks, we find the evidence for increased volcanism that would have led to increased carbon dioxide levels during the Cretaceous. Each one of these yellow layers represents the rain of ash from a volcanic eruption. As you can see, there are multiple layers. All around the globe, we find similar evidence for substantially increased volcanic activity during the Cretaceous. We discovered that the locations of continents and the flooding of the continents is only part of the story of explaining the Cretaceous warmth. A combination of all of the data and the results from climate models strongly suggest that a CO2 greenhouse effect may have played a major role in explaining the extreme warmth of the Cretaceous. This has probably happened repeatedly in the past. If it's happened in the past, it can happen again.
Now, scientists have added a new chapter to the carbon dioxide story. Pat Zimmerman is an atmospheric chemist. He now studies termites. In the wild, their populations remain in check, but Zimmerman believes the accelerated clearing of rainforests and grasslands may lead to a population explosion that could well influence world climate. There already may be as many as 3/4 of a ton of termites for every human being on Earth.
We think that global termite populations could be increasing. An area of tropical forest roughly the size of Connecticut is cleared each year. And when it's cleared, the ecosystem is greatly simplified. The whole decomposer chain is removed, predators are removed, and that allows termite populations to really explode.
Creatures of antiquity, termites have inhabited the Earth for 100 million years. Long studied for their complex social structure, Zimmerman is now monitoring termites for methane, one of a number of warming gases like carbon dioxide. Methane has doubled over the past 150 years, and scientists are concerned about its long-range impact. To measure the amount of methane a termite can produce, the insects are placed in a jar together with a piece of wood. Each jar is attached to an instrument that will analyze how much wood is converted to methane. The primary food of termites is cellulose, found in plants and trees. Few animals can digest it, but termites have evolved one of the most efficient symbiotic relationships in nature. Buried deep in their digestive system is a swarm of microbes that secretes an enzyme to reduce cellulose to sugar. The sugar is then absorbed by the termites. A byproduct of this chemical transformation is methane.
Although this experiment seems pretty simple, nobody had ever done it before. People had realized that termites could emit methane as long as 50 years ago, but nobody had the capability to be able to quantitate the emission rate, and nobody realized that there were enough termites in the world so that that emission could potentially affect the chemistry of the Earth's atmosphere.
The results of Zimmerman's research are intriguing, but evidence also suggests that methane is on the rise from other sources, like swamps and cattle in the increasing cultivation of rice. But methane is only one of the greenhouse gases that now may influence Earth's climate. If these gases continue to increase, they could double the warming effect of carbon dioxide early in the next century, faster and much more alarming than previously thought.
Although this research is in its initial stages and it's still somewhat controversial, there's no question that our Earth and its climate would be completely different if it weren't for the activities of biological sources. Our Earth is a delicate balance between our atmosphere and our biosphere. The emissions from termites illustrate how a single organism has the potential to affect our climate.
Sometime in the 1990s, climate scientists expect to have conclusive proof whether the current warming trend is larger than the normal fluctuations we observe in climate. Climatologist Stephen Schneider.
We in the climate sciences face a big challenge. When are we going to have a global understanding of the climate system, how it will change, and how it will impact upon people and the rest of the planet Earth? The trouble is, we know that we have greenhouse gases increasing. We know that they can have a global effect. It's not new to think that there could be environmental problems. They go back decades. In fact, they go back centuries. The London smogs are a good example, but they were local. Acid rain is another well-known example, but it tends to be regional. What makes the greenhouse effect both unique, interesting, and admittedly disturbing is that it's both global and potentially long-lasting. We have our climate models. They give us a crystal ball, if you will, but they're not perfect. The crystal ball is dirty. And the tough question for us to ask is, how long do we clean the glass before we act on what we think we see inside?
For the first time, man may play an ominous role in the future climate of planet Earth. Although climate changes seem inevitable and the processes that determine it are still not understood, the human species is now a major player in the drama. Today, new tools and technology help scientists assemble the pieces of the climate puzzle. We have now begun to understand the factors that influence the climate of planet Earth. We have uncovered the record of a spectacular past, revealed in Earth's rock, its oceans, the ice and air, and even its life. We have seen devastating ice ages transform the Earth and tropical climates in places now frigid. We have journeyed into space and found clues to our future. Could Earth become a world of fire or a world of ice? A new frontier of exploration has uncovered an Earth that has changed in the past and will change in the future. How much and when are the questions that remain in the perplexing puzzle of the climate of planet Earth.
Annenberg Media. For information about this and other Annenberg Media programs, call 1-800-LEARNER and visit us at www.learner.org.